Right, well, thanks very much for inviting me. By objective possibilities, I mean, at least in part, possibilities, things that could have been the case in some quite non-epistemic sense. I mean, for example, not being a theist, I think that it could have been the case that there were no thinking beings. I mean, maybe, you know, we know a priori that there are thinking beings, but still it could have been the case that there weren't. So that's the kind of possibility which, as it were, is possible for, in a way that doesn't really depend on anything particularly to do with who knows what. I mean, these possibilities come in all sorts of different kinds. For example, I mean, many of these are registered in natural language and sorts of modal terms that we use to talk about them, things like can and so on, are, I mean, they're dependent on context. So in some contexts, it may be true to say that I can speak Chinese in the sense that, you know, by contrast with an elephant, whatever, who's just not got the physical capacity to learn Chinese. But in another sense, obviously, I can't speak Chinese because I never learnt it. I mean, in fact, semanticists within linguistics recognize a category that corresponds fairly well to what I had in mind as what they call circumstantial readings of modal terms like can. I've avoided the term circumstantial because it suggests some kind of dependence on circumstances, whereas one of the types of objective possibility that I'm interested in is metaphysical possibility, which is precisely supposed not to depend on circumstances in that kind of way. But there's a fairly close connection between the linguist's category of circumstantial modality and my category of objective modality. So as it were, we've got a whole family of types of possibility of this broadly objective kind. I'm not going to try to fill in exactly what it takes to be objective. I think it takes probably more than just to be non-epistemic, but well, the idea is that these form some kind of natural family, and I'll say a little bit more about what's involved in them later. Now, this category of objective modality has been subject to quite a lot of skepticism from philosophers, from Hume onwards, and you know, Quine is an obvious person to mention, but one might even think of David Lewis, because his modal realism seems like a way of, well, in his view, rescuing modality for empiricism by of a certain kind by equating it with something completely non-modal, but that's not going to be the subject of this talk. So we've got this kind of skepticism, which of course typically is expressed as skepticism about necessity in some objective sense, but of course, the notions of necessity and possibility are dual, and so, you know, if you think that one of them doesn't make much sense, then you're going to think the same about the other. Now, of course, you know, given what I've said, and given the fact that there are various sorts of linguistic markers which tend to distinguish circumstantial readings from non-circumstantial ones and so on. This category of objective modality is not simply, as it were, something that has been cooked up by philosophers, but even if it's got quite solid roots in, as it were, commonsensical ways of thinking, I mean, you might still fear that it's some kind of, as it were, folk metaphysics, which doesn't really correspond to anything very natural or significant. And some recent criticisms of, particularly the category of metaphysical modality, have been something along those lines. I'm thinking, for example, of people like Ted Sider. Or else you might think that somehow this is not really a way of talking about how the world is, but some more complicated stories might be supposed to obtain, maybe some weird expressivist kind or whatever. And I think one of the things that makes objective modality, at least apparently vulnerable to this kind of skepticism, is the idea that doesn't really have any firm connection with science. One way of, as it were, filling out that kind of doubt that as it were, any scientific basis for this kind of modal talk might be, if you think about the fact that as it were, the harder the science gets, the more it's expressed in mathematical terms, and mathematics is a modality-free zone. I mean, as it were, if you look in a mathematics textbook, you won't see any boxes or diamonds, or if you do see them, they won't mean objective modalities. Of course, somebody might reply to that, but even if the mathematicians don't actually talk about modalities, still mathematics is necessary, so as it were, there's something modal going on there. But I don't think that's a very satisfactory reply by itself, because it doesn't really show that the modal qualification is doing any work in the mathematics. It could just be some kind of extraneous approval that metaphysicians, for their own motives, apply to mathematics. You might think, in the same sort of way as if you had a philosopher who went round sticking gold stars onto some machines, and on the gold star it said, this machine has been approved by a qualified metaphysician. I mean, it kind of might look nice, but it wouldn't actually make any difference to how the machine worked. And so you could think that just calling mathematical theorems metaphysically necessary or something doesn't really do any more work than that. I mean, I think that's in fact a completely mistaken view. But what I want to do in this talk is just to explore a bit the ways in which, as far as I can see, modality of an objective kind is something that is investigated actually all the time within the sciences, and to explain a bit about what's involved in that and why that might, in some ways, not seem to be the case. Since I'm especially interested in, as well, metaphysical modality, which, I'll explain a bit of how I understand that notion, but it's that's some kind of extreme form of modality, which maybe is more radical than the types of modality that are typically explored, certainly in the natural sciences, I want to say something about how this whole family of objective modalities holds together, and what the relation of metaphysical modality is to the other kinds of objective modalities, which are maybe the ones more explored in the natural sciences, and then that will enable me to say something about what happens in the natural sciences. Also, to some extent, casts light on this more radical notion of metaphysical possibility and necessity. So, something that you will find on the handout, which I'm not going to go through in any detail, is a kind of a toy theory of the family of objective modalities, which I've put it in terms of objective necessity operators, but just for reasons of convenience rather than possibility. But of course, necessity and possibility here are always going to be dual. I mean, possibly P is equivalent to not necessarily, not P, whatever particular reading one's giving to the necessarily and the possibly. I haven't given this little theory in terms of possible worlds because the trouble is that by talking about possible worlds, the danger is that we beg questions by building some kind of modality into the account. And if we start talking about impossible worlds, as some do, the trouble is that those are very often taken to be something linguistic. I mean, for example, simply assignments, as it were, any old assignment of truth values to sentences or something like that. Whereas the modalities I'm talking about, I'm not interested here in exploring the modalities that happen to be expressed in some natural language, but as it were, the modalities themselves rather than their linguistic expressions. So the way I've done it, but for purposes of convenience, is to just use a framework of a very simple little theory of propositions, which are understood as non-linguistic things that may be expressed by sentences. And I've done the propositions as, treated them as quite coarse-grained, so they're as forming a Boolean algebra, which means that, for example, the structure of a sentence won't automatically be reflected in any structure in the proposition that it expresses, because the Boolean algebras are defined by all these equations, which in effect identify, for example, disjunctions with negated conjunctions of negated things and so on, and which, where those equations kind of smooth out some of that structure. I mean, nothing very much hangs on this. I mean, you could do it in terms of a more fine-grained theory of propositions, but I think doing it the way I've done it kind of brings out some of the interesting structure more clearly. And by the way, I'm going to understand this for those who are interested as a complete Boolean algebra, which means that you can form conjunctions and disjunctions of its members, even with infinitely many conjuncts or infinitely many disjuncts. And so we've got those kind of infinitary operations of conjunction and disjunction that we can perform on the propositions, and we've also got negation. And then we're going to have various necessity operators, the objective necessity operators, which are understood as being of varying degrees of strength, and perhaps varying amongst each other in all sorts of other ways as well. I mean, I haven't specified much about that. But then we've got a number of what you might think of as closure conditions on them. Oh, and I'm just going to make one structural assumption about how these necessity operators behave, which is that they commute with conjunction. So in other words, a conjunction is necessary in any one of these objective senses, if and only if all its conjuncts are necessary, which, I mean, seems a pretty reasonable assumption for any decent notion of necessity. And then, well, if you're curious, this is written out on the handout, but I'll just talk through it in a very informal way. So there are four kind of closure assumptions that I'm making about this family of objective modalities. One is that there's what one could think of as an identity necessity operator, which is actually a trivial operator which doesn't do anything to a proposition, it just leaves it as it was. So this is in effect, if you like, it's just treating truth as a kind of limiting case of necessity, one where we don't look at any other possibilities than actuality itself. Then there's closure under composition, which is just saying, basically, supposing that we've got two types of objective necessity, which we can call necessary 1 and necessary 2, then it's saying that we get another type of objective necessity by just taking the operator, it's necessary 1, that it's necessary 2. I mean, and the idea is that that's all, if necessary 1 and necessary 2 are both objective, then necessary 1 and necessary, then this composite operator will also be objective. That seems fairly reasonable. The trickiest and I think and least obvious one, which you might have qualms about, is the one that I've called reversal. Which says that if you've got an objective necessity operator, then there's going to be a possibly different objective necessity operator, which kind of reverses the effect of the first one. So it means that if P is true, then it's necessarily 1 the case, that it's possibly 2 the case, that P. So the way to think of this is as a kind of analogy of the relations that we have between past and future temporal operators. So, with past and future, if P is the case, then always in the future, it will be the case that it was the case that P. And similarly, if P is the case, then always in the past it was going to be the case that P is something. So the idea is that if you think of it in terms of what one might call accessibility relations in the sense of modal logic, if you can go from where we are to something that is possible in some sense, in some objective sense, then as it were, you can go back from that possibility to actuality by some objective route, but not necessarily the route that you first take. I mean, the route that you took might have been a one-way street, but there's still some other objective route back to where we are. And then the final condition is just that if you've got a whole class of objective necessity operators, then you can conjoin them so that there's another necessity operator which, if you like, applies to just the things that all of the objective necessity operators in that class apply to. So, I mean, these are not indubitable assumptions, but I think they're fairly reasonable ones, and they kind of provide a sort of some sort of family connection amongst this family of objective necessity operators, because as a way you can do all these operations on them and you get a further member of the family. And for each of these necessity operators, you can define a corresponding modal logic in a very natural way. Basically, all you do is you take the theorems of this logic to be the sentences of the standard language for propositional modal logic that get mapped to the top element, the tautology in the Boolean algebra, by any kind of mapping that treats the truth functions in the obvious way in terms of the operations you have in the Boolean algebra of propositions, and that interprets the box of the modal language by the necessity operator that we're interested in. And if you define a modal logic like that, it will turn out that whatever objective necessity operator you take, its modal logic will be what is called a normal modal logic, which means it has the kind of nice features that as it were, at least you'd expect of a decent necessity operator. Part of my reason for going through this is then to say something about how metaphysical modality fits into the picture. So the way I want to understand metaphysical necessity is just as the conjunction of all objective necessity operators. And the principle 4 that I laid down, it tells you that there is an objective necessity operator that's equivalent to the conjunction of all objective necessity operators, and therefore it will be at least as strong as any objective necessity operator. And a nice feature of this little mini theory is that it tells us something about the logic of metaphysical necessity. In fact, it tells us that the logic of it will be at least what's called S5, which is what most people would like to have as the logic of metaphysical necessity. And just very briefly to say why that's the case. I mean, the crucial axioms that we have to check are these ones which I've standardly labelled T, 4, and B on page 2 of the handout. So axiom T says that what's necessarily the case is the case. And it turns out that that's guaranteed by the assumption that we have this kind of trivial truth operator as a necessity operator. The axiom 4 is that what's necessarily the case is necessarily the case, and that's guaranteed by the assumption that when you compose two objective necessity operators, you get another objective necessity operator. And finally, there's axiom B, that is what is the case is necessarily possibly the case, and that turns out to be guaranteed by the reversal assumption. So in other words, if you just assume that metaphysical necessity is the maximal objective necessity operator, then you can get out all these desirable special assumptions about its logic without putting them into the logic of all the objective necessity operators in general, via its position as the maximal necessity operator combined with closure assumptions on the whole family of objective necessity operators. Okay, well that's, as it were, the picture of the way these objective necessity operators hang together. I'm now going to switch to the second part of the talk, where I'm going to say something about how some kind of objective necessity is in effect getting studied in natural science all the time, even though it may appear not to be. So, I mean, I think there are lots of different examples that one could take, but the case I'll talk about is the case of dynamical systems theory, which is it's a mathematical theory, but one designed for applications in various branches of natural science. I mean, physics, chemistry, biology, engineering. It's applied to the motion of a pendulum, the solar system, the predator-prey relations in biology, or the weather, all sorts of things. And it's also a standard framework for studying chaos. So, I mean, in a way, it's quite overt that what we're dealing with here is some kind of possibility, because you know, if we ask, when we look at the applications, we're in fact going to be told that what we're looking at is the space of possible states of some physical, doesn't even have to be physical, system. But I think it's kind of instructive to look at what's going on in a bit more detail, to see how the modality is entering here, and how what we're getting really is a kind of a modal investigation, as it were, modal in its subject matter, not simply that, as it were, we extraneously award it some kind of modal status from the outside. So let me just explain how these dynamical systems work a bit. So what we have is the set, just from a mathematical point of view, we have some set S. Informally, we're going to interpret this as a set of states of a system when we come to apply it. But from a mathematical point of view, we're just assuming a set S. And normally, we impose some kind of geometrical or topological structure on the state S, because I mean that's how we're going to get some real work out of this dynamical system. But we don't need to worry, as it were, much about just how that's defined in a particular case. We've also got a set T, which is normally either the set of real numbers or the set of integers, and that will be interpreted as the set of what we might call directed lengths of time. When I say directed, the crucial point is that plus 1 and minus 1 are different. Plus 1 as where you can think of as 1 unit of time into the future, and minus 1 as 1 unit of time into the past. And we've got, well, as you might expect, we've got some kind of additive structure on these, on these direct lengths of time. And then the dynamics of the system is given by a set of functions, f of t, where these functions they're indexed by the members of t. So for every directly length of time, you've got a corresponding function f. And the way to understand that is that, and suppose that we're in the system is in state S, then f of t of S is the state that the system will be in t, the length of time t after S. Where of course if t is negative, then that will be a timing factor, but before it was in state S. So this is a a setup in which we're assuming determinism, and in fact we're assuming it in both directions. We're assuming that the present state of the system determines what state it will be in at all future times and at all past times. I mean, we could just make it one-way determinism if we wanted to, but on the most natural way of doing it, it's going to be some kind of two-way determinism. And then there are a couple of very trivial conditions that have to be met by these functions, which are kind of obvious when you think what they mean. F of 0 of s has to be s because f of 0 of s is the state that the system will be in a length of time 0 after it's been in s. So of course we haven't actually had any passage of time, so it's still in s because they're actually talking about the same moment. And then we've also got the f of t of f of t star of s. That's going to be the same as f of t plus t star of s. So this is just, well, this is the state that it'll be in a time t star after it's been in s, and then this is the state that it'll be in t, like, and t after it's been in this state. And so of course that's just the state that it'll be in length of time t plus t star after it's been in state s. So those conditions, they're just for the dynamics to make sense. And we don't need to worry about as much, but if we're thinking, if the set t of direct lengths of time, if that's the real numbers, then we've got some kind of continuous dynamic that will be given by differential equations. If it's if we're just using a set of integers, then it's a discrete dynamics, and it'll be given by a set of difference equations. But nothing I'm going to say depends on the details of that sort of thing. So that's what it looks like mathematically. And one thing to say about the modal aspect of this is, I mean, we've obviously got a temporal aspect as well, because we've got these lengths of time t here. But the modality isn't, as it were, exhausted just by the temporal relation, because, I mean, we could think of an orbit as being, well, because we can associate with any particular state S, we can associate something called an orbit, which is a set of states, and it will be the set of states that the system is in at some time or other, if at some time it's in S. So as it were, the set of states that it goes through in the total infinite history of past and present. And the critical thing is just that with most of these dynamical systems, an orbit does not exhaust the total set of states S. In other words, it's not the case that, as well, sooner or later you're going to go through every single state in S. And that means that whatever state you're in, there are going to be some states in S which you never go through. So in other words, the set of possible states of the system is not typically exhausted by the states that sooner or later it will go through. So we've got a genuine distinction between sort of time and modality here. Now, it's quite instructive to think about how these states of the system correspond to something like possible worlds. I mean, there are some obvious differences because these systems are not usually meant to exhaust the whole universe, so as it were, they're individuated in a way which doesn't take account of everything in the universe, but you could still think of them as kind of mini-worlds which just look at some aspects of things. I mean, they're the comparison with worlds is not completely apt, because after all, a world is supposed to encapsulate a total history of the universe, or whatever system we're talking about. Whereas these states are instantaneous states. So in fact, it would be more accurate if we were comparing this to something like the semantics of modality in terms of possible worlds. Actually, to think of the semantics from a modal temporal logic, where we have both modal operators like possibly and temporal operators like in the past and in the future. And then in the semantics, typically not always you're evaluating formulas at a pair of a world at a time. And so you might think that these states are something like just a world-time pair, but even that isn't completely accurate, because with some of these dynamical systems, they may cycle. I mean, in other words, they may go through the same state many, many times, and so there's something more qualitative about these states. But although what's going on here is a little bit different from what you get in something like modal temporal logic, it seems to me that it's also has very, very much the same kind of flavor. And in fact, it's possible to define a kind of modal temporal logic in terms of the dynamical system. So if you take any given dynamical system, you can kind of read of it something like a modal temporal logic. And I don't want to go through the details of this, but I'll just give you a kind of feel for what's going on. I mean, the key thing is that just as you can think in the modal case of propositions are treated as, if you think of associated them with sentences, they're treated as something like sets of worlds, and in the modal temporal case, what you look at is sets of ordered pairs of worlds and times, because you want to be sensitive to when you are, as well as which world you're in. The corresponding kind of notion of proposition, in some sense, maybe it's not exactly in the standard sense, that fits the dynamical systems framework, is where you treat the propositions as sets of states. And then the dynamical system itself automatically gives you interpretations for just the kind of operators that you want. I mean, so with the modal operators, the diamond and the possibility and the box and necessity, there we just interpret them by what holds in some state or what holds in all states, and so what we're doing is we're evaluating sentences at states in just as we evaluate them in analogous logics at worlds or at world-time pairs, and so we can define some kind of future operator using the dynamics of the system to say that, to talk about whether, in the future such and such will be the case when you're in state S, and a whole lot of fairly standard temporal operators like that. You can also have metric temporal notions where you have an operator like g of t, where t is one of these direct lengths of time, which means as well, exactly t from now such and such will be the case. You can also, as it were, encode the topology or geometry, whatever mathematical structure it is, that you've got by just having, in fact, operators which tell you whether a given sentence expresses something, something with a suitable mathematical property, like whether the set of states that it's true in form an open set in the topology or whatever it is that you happen to be interested in. And then we can do a certain kind of quantification in this language by quantifying inter-sentence position. So, which in effect is interpreted as quantification over propositions, which are in turn being thought of as sets of states. And it turns out that with this kind of apparatus, you can in very, very natural ways express standard notions of dynamical systems theory. I'm not going to go through any of the details. You can ask about the discussion if you want. But what I want to emphasize about this is that this is not, as it were, something where you really have to twist the mathematics into some kind of modal shape. The structure of mathematics immediately lends itself to these kinds of interpretations. And I mean, the flavor of it is very similar to the way in which you can just, as well, when you've got some kind of possible worlds model, you can just, as it were, very, very straightforwardly interpret it, use it to interpret modal operators or modal and temporal operators if you also have a time structure to it, and so on. So it feels as though all that is going on here is that we're making a bit more explicit the modal and temporal dimensions, which are built into the intended applications of the mathematics. And so, I think this helps to understand how a piece of mathematics, which in itself has got, as it were, no modal or temporal content at all, can nevertheless, in its application to some particular physical system, be used in studying the modal and temporal dimensions of that system. In the same way that if you look at a theory where you've got quantification over worlds, possible worlds, if you just look at at possible world semantics as a piece of mathematics, like any other piece of mathematics, it will look totally non-modal. But as soon as you, as with intended interpretation, it's not that you're avoiding modality; it's that you're studying it, but in this this mathematical form. And I think exactly the same thing is going on with dynamical systems theory, and I take it all sorts of other studies of phase space, which you get in all sorts of branches of science. So, it's not that somehow the science is eliminating the modal dimension. It's making, in effect, very strong assumptions about it in treating it in this mathematical form. So, I think some of this comes out when one thinks about the question of contingentism versus necessitism, which is something that I addressed in my book Modality as metaphysics, where what we're concerned with is how to treat issues of existence in a modal setting, and in particular whether existence, understood in the most general sense of just being something or other, is necessary or contingent. And if one takes as well, the possible worlds approach really seriously, so that one can just talk about all these worlds, with just using quantification and no modal operators, but as we're just in more purely mathematical language, about possible worlds and their domains, the individuals that exist in them, and so on. One's in effect working with the assumption that as well there are all these individuals there to be quantified over, and that's why the contingentist who thinks that existence is a contingent matter has to somehow treat the possible world's semantics with a fairly considerable dose of salt. And I think something similar is going on with dynamical systems theory. But it's typically not going on about the existence of the individual so much as with the existence of these states, because that's what is most naturally quantified over in just making the modal dimension of the mathematical the application of the mathematics explicit. And well, I don't want to go into the technical details about it, but if we're talking about the individuals, there's a crucial formula that necessitists and contingentists divide over is the one that I've labelled NNE near the end of the handout, which says that necessarily everything is necessarily something, which that's what a necessitist will accept and a contingentist will reject. And if one looks at the semantics that I gave for the dynamical systems theory, it has the equivalent of that, but at the level of propositions rather than states. Rather than individuals, because that system doesn't have quantification over individuals. So, as we're roughly speaking, the formula at the end of the handout, which I've labelled NNEP, is the thing to understand here is that the formula necessarily U if and only if V. That's the equivalent of U equals V, but it's just that U and V are sentences rather than names, so the grammar has to be different. But these are sentences which are being interpreted as standing for propositions, i.e. sets of states. And since the box quantifies over all states, the only way we can have necessarily U if and only if V is if U and V correspond to the very same set of states. And so this is, in effect, a kind of propositional identity. And so NNEP is saying that necessarily, if you like, every proposition is necessarily some proposition, and which is, I mean, that's the equivalent of the necessitist claim, but about propositions rather than individuals. But I mean, many contingentists, such as Stolmaker, for example, they want to be contingentists not only about, as it were, the particulars, but also about propositions and properties and so on. And so something like NNEP would be, it's a controversial claim metaphysically, but it's kind of built into the way that the dynamical system is being treated in the mathematics. And I mean, I think there are all sorts of other consequences of the treatment that I gave. For example, that you'll get a logic of S5 for the modality, and these. So it's not that there's something, as it were, just purely neutral about the mathematics. The mathematics is building in all sorts of assumptions, or rather, not strictly the mathematics itself, but it's the assumption that one can just use this mathematics to reason about possible states of the system in a certain way. Has all these assumptions built into it. I mean, of course, you could then say, well, we have to take the mathematics with a dose of salt, or the application of the mathematics with a dose of salt. But it's not that what we've got is some kind of, as it were, modality-free investigation. We've got an investigation which is, up to its neck in modal assumptions, which are behind the free application of mathematics to reasoning about the possible states of the system. So, sorry, that's very programmatic, but that's the way in which it seems to me that, in effect, an awful lot of science is, in effect, an investigation of modal questions under certain very significant modal assumptions, even though it looks as though all you're dealing with is some piece of mathematics, and how could that have modal consequences. I'll just finish by saying a couple of things about how this relates to the question of metaphysical necessity, because, of course, the kind of necessity that we're dealing with when we're talking about possible states in the physical system is probably something much more restricted than metaphysical necessity. We're not interested in, as it were, possible situations, if there are some, where the laws of nature break down. And in fact, if you think about the kind of applications that I was talking about, the dynamics of the system doesn't straightforwardly follow just from the laws of nature. It's also, I mean, there have to be all sorts of other assumptions in place for the pendulum to follow to behave as a pendulum, and so we're dealing with something quite restricted. And you might wonder, well, if we are investigating objective possibilities in the science in this sort of way, but they're so restricted, what does this have to do with metaphysical possibility and necessity? So I think, there are really just 2 points I want to make about that. One is that, given the account that I gave of metaphysical modality, if anything is possible in one of these more restrictive senses, providing it's an objective sense, then it is metaphysically possible as well. as it were, the metaphysical possibility is the most extensive form of objective possibility. And so, all the kind of empiricist worries about, well, how can we know that something is possible if it isn't actual, and so on. I mean, they're already they're already answered for a metaphysical possibility if we take it that the science can answer them for these much more restricted forms of possibility, but because of the inference from restricted possibility to unrestricted possibility, basically. Of course, that doesn't tell us how that we can get any interesting conclusions about what's metaphysically necessary as opposed to what's metaphysically possible. But I think the case of necessitism and contingentism is typical in that it shows ways in which we actually don't, as it were, miss very much in evaluating by looking at relatively restricted possibilities, because the necessitist view is that that being something is not a contingent matter. So, for example, that even if my parents had never met and I'd never been conceived or born, that I would still have been something, I would still have been a possible human being. And of course, I mean, that the contingentists hate that idea, but the point is that the relevant alleged counterexamples to necessitism are ones which are quite easily physically possible. I mean, they just involve things like my parents never having met. I mean, that's a physical possibility in some sense. And so, as with the debate between necessitism and contingentism, it can to a very large extent be carried out just looking at much more restricted physical possibilities. Because, I mean, if the necessitist doesn't have a good answer to this objection, then necessitism is gone anyway, and it's gone just by looking at these physical possibilities. And if the necessitist does have a good answer to these, as it were, most blatant of the putative counterexamples to necessitism, then there really isn't much motivation for being a contingentist, because, I mean, as it were, all the virtues of theoretical simplicity and so on are on the necessitist side. The case for contingentism is just whether there are, as well, the simply undeniable evidence which refutes necessitism. And if there is such evidence, it's the evidence which concerns, as well, relatively easy, close physical possibilities. And so, so in a way, without having to worry about these more far-out possibilities, we can probably settle the necessitism and contingentism debate just by looking at the kind of objective possibilities which are investigated within natural science. Okay, I've been going for much too long, so I'll shut up.